Okay, so far we discussed about the three-dimensional presentation of molecules, and we realized that is stereochemistry. But stereochemistry not only deals with the three-dimensional representations, but also all the properties of molecules, especially organic molecules, where a three-dimensional structure is necessary to explain. All these matters will comes under stereochemistry. So one of the most important properties which we have to understand by using three-dimensional structure or stereochemistry is stereoisomerism. So you have learned what is isomerism, especially in your previous chapter there is structural isomerism. So structural isomerism is nothing but the same molecular formula but different structural formula. So that gives you structural isomerism. Here the molecular formula is the same and also the structural formula is also the same. So the difference is the spatial arrangements of atoms and molecules. So different isomers have the same molecular formula, same structural formula, but different spatial arrangements. That isomerism is called stereoisomerism. Okay, so we will see what is stereoisomerism by seeing the simplest another simple molecule, organic molecule, which is ethane. So here I have given two representations. These two representations actually represent ethane molecule. But my question is, can you see any difference between these two representations? So let's examine one by one. So in these representations, this is front carbon, the first carbon atom, which is labeled in red color, and all the red hydrogens are bonded to this carbon atom. And this one is the second carbon atom, which is I labeled in green color, and all the green hydrogens are bonded to the second carbon atom. And in this representation, this red hydrogen atoms is very close to the green hydrogen atoms. So all the hydrogen atoms are very close to each other. You may feel that there is enough distance between these two hydrogen atoms, but that's only for the sake of understanding. In reality, you know that we are dealing with molecules or atoms, so that might be in angstrom units or nanometers. So there won't be this much space between the atoms. So these atoms or groups are very close to each other. So that makes a crowded atmosphere in this representation because all the hydrogen atoms are very close to each other. So that will generate a steric hindrance. So what is steric hindrance? That you will learn in your previous chapter. So something related to the crowdedness. So what happens? These crowdedness create a discomfort to the molecule. So that means the molecule is not completely stable. So not stable means its energy is higher. Okay. So when it comes to this representation, again this is ethane molecule. So we have red carbon, front carbon here, and all the red hydrogens are bonded to this carbon. This carbon is bonded to the second carbon atom, a single bond. Second carbon atom is labeled in green color, and all the green hydrogens are bonded to the second carbon atom. But the difference is, here the hydrogens are maximum apart. They are situating far apart to each other. So compared to this structure is more comfortable. Means the molecule feels more stability. So that means lesser energy. So that means if you compare these two structures of ethane, this structure is more stable than this structure, or this structure has less energy than this structure. So that means these two are different structures with same molecular formula, same structural formula, but different is in the spatial arrangement of atoms or group of atoms. Now, so this one is less stable with higher energy. This structure is highly stable with the lower energy. How you can get this structure from this one or this structure from this one, or how these structures are interconvertible? You can get this structure from this one or vice versa simply by rotating this carbon-carbon single bond. So if there is a carbon-carbon single bond, free rotation along carbon-carbon single bond is possible. So if you again examine these two structures, in this structure and the first structure, the back carbon, the arrangement is the same, right? But the front carbon, if you rotate this front carbon in direction, for example, clockwise direction, so if you rotate it up to here, this hydrogen will come to here, this hydrogen will come to here, this hydrogen will come to here. So simply by rotating a carbon-carbon single bond, you can get this structure from this structure, or these structures are obtained by the free rotation along carbon-carbon single bond. So they are isomers because they have the same molecular formula, same structural formula, but different spatial arrangements. They have different energies, stabilities are different. Okay. These kind of isomers are called conformers. Very important. Conformers. 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 So what are conformers? Conformers are stereoisomers. They are stereoisomers. We are dealing with the stereoisomerism, right? So conformers are stereoisomers obtaining by the free rotation along carbon-carbon single bond. So if you get stereoisomers simply by rotating a carbon-carbon single bond, those isomers are called conformers. Okay, and this isomerism is known as conformational isomerism. So this isomerism is called conformational isomerism, which comes under stereoisomerism. Now take another example. So we already discussed this one, trans-2-butene and cis-2-butene. Okay, so here what is the difference between trans-2-butene and cis-2-butene? So I have explained in previous slide. In trans-2-butene, these two CH3 groups and these two hydrogen atoms, they are opposite to each other, right? And in cis-2-butene, these two CH3 groups and these two hydrogen atoms are on the same side. So this is cis representation, this is trans-butene, trans representation. Okay, so what is the difference between them? They have the same molecular formula, like C4H8. This is also C4H8. They have same structural formula also, because the bonding is the same, means the way atoms are bonded is the same, but they are different in their spatial arrangements. These CH3s are opposite here, these CH3s are on the same side. Okay, so they are stereoisomers. But compared to the previous stereoisomer which we discussed, like conformers, here you cannot get this structure by rotating this structure. You cannot get this structure by rotating this carbon-carbon double bond. Why? Because free rotation is not at all possible on a carbon-carbon double bond, because we know that in a double bond we have a sigma bond and we have a pi bond. So pi bond is sideways overlap. So because of the sideways overlap, you cannot rotate this carbon-carbon double bond. So that means free rotation is not possible. So this structure is obtained by this structure, not by free rotation. Then how you can get this structure? If you have to get this structure, you have to break this bond and you have to form another new bond. So if you want to get cis isomer from trans isomer, you have to break the bond and you have to form another bond. Okay, so the structures are interconvertible, like restricted rotation along carbon-carbon double bond. So restricted rotation means no free rotation. Then how you can get it? You have to break the bond and you have to form a new bond. Okay, such kind of stereoisomers are called configurations. Okay, so configurations are stereoisomers obtained by the bond breaking and bond formation, or obtained by the restricted rotation along carbon-carbon double bond. So the previous one was conformations. So conformations are isomers, stereoisomers obtained by the free rotation along carbon-carbon single bond. But here it is configurations. Configurations means they are stereoisomers obtained by the restricted rotation along a carbon-carbon double bond, or bond breaking and new bond formation. Okay, and this isomerism is known as configurational isomerism, and especially this particular one is known as geometrical isomerism or cis-trans isomerism. So if I am going in the reverse order, Cis trans isomerism is geometrical isomerism, which is configurational isomerism, because you are getting the isomers by breaking the bond and formation of new bond. And this configuration isomerism belongs to which isomerism? Stereo isomerism, because they have the same molecular formula, they have the same structural formula, they differ only in the spatial arrangements of atoms or groups. Okay, so put it together. Stereoisomerism. What is stereoisomerism? Stereoisomerism is isomers having same structure but different spatial arrangements of atoms or groups, right? Stereoisomerism can be classified into two types. One is the conformational isomerism, which is obtained by the free rotation around carbon-carbon single bond. The other one is the configurational isomerism, which is obtained by the restricted rotation along a carbon-carbon double bond or bond breaking and bond formation. The configuration isomerism is again classified into two. One is geometric isomerism or cis trans isomerism, which we discussed just before. The other one is the optical isomerism, which we will discuss later in this chapter. Okay, so this is the classification of stereoisomerism, conformational isomerism and configuration isomerism. Configuration isomerism is again classified into geometrical isomerism and optical isomerism. Okay, so this is for you. You try to figure out what is the difference between conformation and configuration. So what are the differences, or differentiate between conformation and configuration. Okay, so this is all about the first lecture on stereochemistry. I hope you understand this one. I will arrange a Google Meet with you, and in that meet we can discuss if you have any doubts. Thank you for listening to this lecture.